An introduction to graphs. Graphs can be expressed in two ways, either pictorially, as a bunch of dots, which we can name A, B, C, and D. These dots don't have to be connected by lines, edges, which I'll name E1 and E2. Okay. Already hinted at it, but A, B, C, and D are our vertices. E1 and E2, the lines connecting the dots, are our edges. Okay. This is one way to represent a graph. Another way to represent the graph is using set notation. So V equals the ordered pair, G equals the ordered pair V, E, where V and E are the set of all vertices and the set of all edges. So we can literally represent this graph by the vertices, set of all vertices, and the set of all edges, E1, E2. It's one way to represent the graph. Okay. Again, two ways. Both of these are equivalent. Both have their uses. A lot of times with the applications of graphs, it's much easier to look at them pictorially, as we've done here as a diagram. But a lot of times when we're proving information about graphs, this set notation can be more beneficial. As we've seen before, using sets to prove things can be extremely helpful. So that's what we'll be doing most often when we're trying to prove different properties that a graph might have, or just prove general concepts about graphs. We'll use a set notation, and if we're trying to look at commonalities or similarities between two different graphs or supposedly different graphs, then the pictorial representation can often be helpful. One thing that is especially nice about graphs, which we'll see more of, is with graphs, distance does not matter. Only connections. If you've heard of topology, that's the study of very similar topics in which the distance doesn't matter, just matters how things are connected. This is even more simplistic than the topic of topology, though. In graph theory, all we care about is what is being connected, and in some cases, how many ways they're being connected. A quick application, kind of a classic application of graph theory, is if we're discussing airlines, or air travel in general, let's say. Anytime you have an application that you want to denote in terms of a graph somehow, the idea is we need to figure out what is being connected, those will be our vertices, and what those connections are. So the connections themselves. Figure out both of those, then all we have to do is show those connections visually. So, talking about air travel, let's say we've got this scenario in which we have Kansas City, Chicago, and St. Louis. You can get from Kansas City to Chicago, Chicago to St. Louis, and St. Louis to Kansas City. And we can show connections just like this. Okay? But this is a little unrealistic. If we're just showing the connections and the fact that I can get from Kansas City to Chicago and Chicago to St. Louis, then this is perfectly acceptable. But in actuality, there's going to be several more ways to get between these different cities. Right? There's dozens of flights a day between some of them. that can be represented in the same way as we have over here. But, again, we're talking about multiple flights. Each flight is a connection, so we're talking about multiple edges here. So I can denote a very similar graph, like this, in which we have multiple edges going between these different cities. Okay. So in this case, 3 different flights between Kansas City and Chicago, 4 between Chicago and St. Louis, and 2 flights between Kansas City and St. Louis. This idea still holds if we have little old Omaha up here. And let's say, for example, you can only fly between Omaha and Kansas City and Omaha and Chicago. In other words, there are no flights to get from Omaha directly to St. Louis. We can express it in this way. Let's say there's 2 flights between Omaha and Chicago and 4 flights between Omaha and Kansas City. There's an obvious downside to expressing the graphs in this term, in this way, and that is it gets pretty confusing. Again, if we're talking about the actual number of flights between Kansas City and Chicago and each of these other cities, we're talking about several additional edges that need to be drawn, and it's just going to get very, very hectic, very, very fast. Whereas over here, we're simply showing the fact that I can get from Omaha to Kansas City directly, and I can get from Omaha to Chicago directly, but I cannot get from Omaha to St. Louis. That's much more clear on this graph on the left than it is on the one on the right. This leftmost graph is called a simple graph. In a simple graph, there is at most one edge between any 2 vertices. So this graph represents a simple graph as well. There's at most one edge between any 2 vertices. Notice that D does not have any edges connected to it, but that's okay. There's at most one edge. And down here, we call this a multigraph. Not a very exciting word, should be pretty intuitive. Multiple edges, single edges, simple. Much more simple of a graph. In addition to these phrases, now this is going into the next section a little bit, but in addition to simple graphs versus multigraphs, we can also get into directed graphs, which again makes a little bit more sense as far as flights are concerned, right? In actuality, each of these flights is going a particular direction. So instead of talking about just the connections between these 2 cities, I can assign arrows to these edges, and you can see it's not very effective here. I can assign arrows to these edges to denote that these are directed flights. In other words, this now shows that I can go from St. Louis to Chicago, but not Chicago to St. Louis directly. Okay? By adding the arrows in there. Similarly, I can go from Kansas City directly to St. Louis, but not St. Louis directly to Kansas City, and so on. Now, if you have a directed graph, the norm is for all of your edges to have a direction, even if that direction is something like this. And most textbooks will go ahead and denote something like this. You notice that there is a double arrow between Kansas City and Chicago, meaning I can go this way or I can go this way. Most textbooks would denote this as multiple arrows. So this would be, in turn, a multigraph by setting those arrows in both directions. Okay? But again, with directed graphs, oftentimes there will be directions assigned to each edge, not just a couple of them. Okay? As usual, if you have any questions, please feel free to email. Otherwise, the rest of this section just deals more with the terminology, but when we get into section 2, we're going to be doing a few more problems, but again, just discussing some terminology that's going to be used with graph theory. That is going to be the newest aspect for most of you. It's just the terminology. Some of it's intuitive, some of it is not. If you have any questions, though, again, please feel free to email me.